Okay. First, I would like to thank the organizers very much for giving me this opportunity to speak. So today I'm going to talk about ongoing work that we're writing now, haven't finished, with Jordan Kostler, who is also here, and another two students, Xi Zhihan and Zhao Yang at Stanford. Oh, I guess I can. Sorry. That'd be better. Okay, so first let me explain the motivation of this work. Although this is not particularly about holography and our tensor network approach of holography, it's certainly inspired by that. So basically, if you use one word to summarize the lesson we learned from the previous talks about holographic duality, I would say it means that GR is from quantum mechanics, and more particularly from quantum entanglement. I think Lenny has a recent paper said that. Said GR is from quantum mechanics. That's what Lenny said recently. Okay, so I would like to call it QE more precisely. Anyway, so if we think about this, then of course a more important part of the geometry is the causal structure. So in the classical case, the causal structure is sort of simple. Means I give you a metric of the space-time that determines whether 2 points has distance that are space-like or time-like, and then that determines whether one event can influence the other. So if I have y in the future icon of x, then something happen at x can influence y. Since the relativity principle tells us that the space-time geometry should be determined by an observable way. It should be determined by how we measure it, and it should depend on the dynamics of the system. Then when we think about quantum mechanics, we will want to give up on this conventional view when we think we start in the definition. We already have a time that's determined, it's a parameter that's given, and then there's a Hilbert space, and you may have different choice of the time, but you have to put one of them in your definition. So you would like to do better and think about how do we measure causal influence between events in quantum systems, and does that teach us something new compared to the classical case? That will be that's the motivation of this work. So let's start from an almost trivial example to see why in quantum mechanics the problem is a little different from the classical case. So let's think about two operators acting on two qubits. So these two operators act at the same time at two different locations. The two qubits are at two spatial locations. Then these two operations are considered as two events that are space-like separated. So they cannot influence each other. They are independent from each other. That's true. But if you think about a system where I know a little bit more about the initial state, so I know the initial state is an EPR pair between the two qubits, then you know there is a general mathematical fact that any operator acting on qubit 1 is equivalent to an operator acting on qubit 2, which is just some operator defined by the transpose of the matrix. So that means that action of V1, V2 is equivalent to doing nothing to qubit 1, but applying two operators sequentially in the qubit 2. And this applies to anything you do, right? It applies to any operator you apply here. So if that's true, then that means if you always restrict to this subset of initial states, then there is no physical observable meaning to distinguish these two situations, although one looks like space-like separated events, one looks like time-like separated. So this is an example why things becomes different from our intuition when we look at quantum systems. And we're going to look at other examples. So let's say you see this picture a lot in the talk yesterday, many talks yesterday. Somehow in quantum information, people like to have time horizontally, although I prefer to have time running vertically. So this is the only picture where I have time horizontally. So this is a quantum circuit where you have qubits and then you have some gates applying to them and so on. But is it always obvious which direction is time if I just tell you this? It's not always obvious. Let's think about an example. Say you have these examples of perfect tensors. Sorry, I should give you definitions of them. What that means is, I learned them from this happy paper a few years ago. I think three of the four authors are here. So you have a tensor which is unitary from left to right, but it's also unitary from these two, bottom to up, from these two to the other two. Well, they also have the third equation, which says it's unitary between the diagonals to the other diagonal. But here we are only going to use the one that's from left to right and the one from bottom to up. So from bottom to top. So if you take these tensors and couple them this way, then you can interpret that as a particular circuit where every gate is this perfect tensor. But and that will suggest that there is a light cone structure like this. Like what you do here will influence what you do later, but not the other way. Like what you do here will not influence things backwards. But you can give the same network a different interpretation. You can say, what if I look at things I do here, and I look at the vertical direction as time? Then it seems like some operator here can be conjugated by these unitaries, and then operator here is the same as operator here. So it looks like the light cone can run vertically rather than horizontally. And these are just, they are physically very different systems, but they are just mathematically, you're doing the same calculation. Like you have this number of qubits, you apply this circuit, or you have this number of qubits, you apply the circuit upwards. But actually, these two systems should be equivalent. What you calculate should be independent from the interpretation. So this is another example where we need some better understanding on what is the observable way to define the causal influence. And some more examples comes from tensor networks in relation to holographic duality. So the discussion about tensor networks in holographic duality started from Brian Swingo's work, and where he discussed the relation between MERA and the bulk of ADS-CFT, of the hyperbolic space in the bulk. But there is always this puzzle to me that whether this MERA should be thought as a de Sitter space or anti-de Sitter, which means that we know the MERA are made by unitary gates and isometries. So it's natural to think that as a quantum circuit. So this direction is like time, and there is like light cone, all these things. But on the other hand, you would like to think about tensor networks that gives you like minimal cuts, that gives you entanglement entropy, which is like thinking that as a spatial slice. So this was partially this problem was partially resolved when you look at this happy tensor networks and the random tensor networks that we studied later, where you have better symmetry because the tensors have a nice symmetry, and you can view them as isometries in different directions. So it looks more space-like because it doesn't have a particular light cone direction. But even then, you have the same kind of question. Like I have isometries from in this network, I have isometries from the minimal surface to the corresponding boundary region. That's why that's why they can prove this Ryuta-Yanagi formula in this case. The entropy is equal to how many qubits you cut at this boundary. But that seems to suggest that there is some like if I do something here, I will influence things here and gradually and there, like following this bitstrise Matt talked about. It looks like there is a sense that there is a time going on. But on the other hand, we should think that all these things are in space. Okay, so the question is whether we can define some way to measure the causal structure and whether that solves these puzzles. Okay, so now let me. So that's a sort of a long motivation. So let me explain what we propose to do. So let's first figure out what is the general setup. So in these two kinds of examples I talked about, like an ordinary time evolution case, or like a tensor network describing the holographic state, you can put them in the same like a mathematical form. So let's look at the time evolution. So what in general in a quantum many-body system, what we do is we do something at a given space-time point or a given region, and then later we evolve the system some more, and then we do something else there. And when I say do something, it may means you change the parameters in your Hamiltonian, or it may means you couple something else to it so that you are entangling your system to an apparatus. So these most general things you can do in different locations. And then after all these things, you collect your measurement results so you always trace over your physical system. And then like you get some probability of reading out some results. So in general, the circuit always looks like this. And since we are interested in the case of two regions, let's restrict to like I'm only doing something to two of the regions in space. Actually, this looks a little too bright to me. Is this better? So because I feel I'm getting blinded. Okay, so actually you can view this in a different way by thinking the whole thing, the whole time evolution with these insertions of your operators, the whole time as a state. And then you always contract it with the same state, the bra and cat. But then what is in the middle is your initial density matrix. And this line just means you trace over the final state, so it's like a maximally mixed state. And in general, if you do post-selection, you can put a non-trivial state there. But the structure of the thing is always like a bra and a cat, of the same as an inner product of something in the middle, which is the boundary condition, which in this case is just determined by your initial state. And the same structure applies to the case of, say, a holographic network or any tensor network that describes the quantum state. In that case, I always do something to these tensors in the bulk, like I adjust them a little bit, or I apply some operators to the links, and then I calculate the expectation value. I calculate the norm of the corresponding state. So that's the same structure, except that now what you put at this boundary here is just a maximally mixed state, because you are doing just calculating the ordinary norm. So now we would like to define a measure of the causal influence, which clearly should be some measure of correlation. It's related to correlation between the two sites, but it cannot be just correlation function because you want something that's one directional. So the definition we take is you put a unitary at a site X, you insert a unitary at a link X, and you put let's say Hermitian operator for site Y. And then you calculate you put in these two things, and then you calculate this quantity, and then you compare it with the case without the unitary in X. So this is measuring whether a unitary operator applied to X influence anything in any physical quantity at a point Y. So let's take this may look a little abstract, so let's take the simplest example, which is the ordinary time evolution. So you think about the time evolution and you discretize time into this kind of circuits. So this is just the standard way you do Trotter decomposition. You have these qubits, and then this upwards is time evolution. So you have two qubit gates applied to them. And in that case, then if I insert a unitary operator acting on that qubit here, then and measure some operator at Y, then the result will be independent from Ux if Y is outside the light cone of X. It will only depend on Ux if Y is in the future light cone. So in the simplest case, it will just reproduce what we are familiar with. It's reproduce the light cone structure. So if you take Ux to be something infinitesimal, this is actually just like a linear response theory. We know like if something happened at time X, then it will not influence anything earlier. It will only influence things later, and the influence is related to commutators. Okay, so this is just the simple case. So in the more general cases, like in a holographic state or something, you can do something more complicated to your system, like coupling it to some apparatus and so on. So in a more general case, the structure is the same. You always identify two links in your networks, and which represents two qubits. And then you apply some unitary to the first one, and then you put some Hermitian operator in the second, and then you measure, you calculate the value of this whole thing. So it's a state on the left that's modified by these operators, and then you always have a boundary condition in the middle, given by some density operator, and you calculate this norm. And so the same quantity. So what I just want to emphasize that this quantity is well defined without first giving an interpretation to the network. You don't need to tell me like this direction is time or that direction is time. That's what usually happens when you calculate the response function. But here, I just need to know these two events, and then I insert things there and evaluate this particular correlation function. So let's look at some more examples and to understand what is non-trivial, what non-trivial things can happen here. So this is just the trivial case when I say like you reproduce the light cone, like only when y is in the future light cone of x, you get a non-trivial influence. But even in this case, there is something interesting can happen. Like let's consider a state. Let's consider a particular initial state, such that the initial state, when you trace over some complement region A bar, then region A is in a maximally mixed state. So region A is maximally entangled with the rest. If that's the case, then you do the same experiment. You do some unitaries at y, and then you put an x, say here or here. You put x here. Then you say, I want to see whether some unitaries here will influence x. Naively, it's in the future light cone, so it should be influenced. But actually, it will not influence anything because the unitary can just you can just push that unitary to the past and get it canceled with this complex conjugate. So what happened? I mean, in other words, the unitary applied to a maximally mixed density matrix doesn't do anything, right? So you see that like actually the future light cone of this point can be removed by preparing a particular initial state. This is similar to like the very simple example we showed at the beginning. Like the causal structure is independent. Sorry, the causal structure depends on the initial state. You can choose a particular initial state to remove part of the future of some events. And that's one important feature of this causal influence. And another important feature is it's non-local. And that can be seen in this simple example of the quantum error correction code. We can think of the error correction code like you encode 1 qubit into 3, let's say, or 1 qubit into 3. And we can think of this encoding as like a time evolution. Well, you do that in your lab, and you have a time evolution that does the encoding. Then you can ask whether there is a causal influence from x to y, which means like I put a unitary here and ask whether that changed anything in the measurement of this single qubit y. Of course, we know like the quantum error correction condition tells me the influence is trivial. Because I mean that's why the errors can be corrected. Like you do some unitaries here, it doesn't change anything for the one site reduced density matrix stays to be maximally mixed, and it doesn't know anything about the unitary here. But if you look at 2 sites or 3 sites, then you know that unitary. Yeah.
So actually, I have a question about the previous slide where you said you cannot see it, but if you would not put a unitary but some kind of a measurement, you would be able to see it.
That's exactly the point, yes. So that's why when we define the causal influence, we need to require that we put a unitary operator in the first point and measure something in the second and see whether there is an influence of the first. It's exactly the key point is if you put 2 operators that are not unitary, then you are just measuring a correlation function. And we know even for space-like separated points, you can have a non-trivial correlation. So the key to distinguish causal influence to other kind of correlations is to require that the cause is unitary. Only in that case there is a difference between past and future.
But wouldn't it be enough to say it's about causal influences? Like any operation you could do just based on certain, like discarding the system and putting a flash qubit or so?
I think if you do that, I mean, if you require the thing here is trace preserving, no, still the influence can go both ways. It can go to future or the past, because measurement is just a special case of the trace preserving maps. Yeah. Yes. So the fact that there is a difference between future and past is only true when you have this point when this is unitary, and when the future contraction is given by a maximally mixed state, and the past is not maximally mixed. So the difference between future and past really comes from the initial state being not maximally mixed. As you see in this example, that when you have a past state that's already maximally mixed, you basically like burn the system, and then you cannot have any non-trivial dynamics there. So there's no difference between past and future. Okay, so going back to this quantum error correction code example, you see this is an example that tells me there's a key difference from the classical case. So in the classical case, if I give you spatial regions and say, does this region, anything happens in this region influence anything in that region, then you just need to look at pairwise points. Like if all the points are space-like separated from X, then the whole region is also space-like separated from X. But this is an example that each point, like each single site region, is sort of space-like separated from X, because like things you do doesn't influence anything in single site. But the union of them, which are the regions with size 2, are actually time-like separated from X. That's the key difference from the classical case, which tells us that the quantum causal structure can be very different, very rich. So something very similar to that, of course, happens to holographic states. Now we understand that this mapping between bulk and boundary has quantum error correction properties. It's not surprising that something very similar to the simple example happens. Like when you consider two links in the holographic tensor network, and you ask if I do something here, insert a unitary, do I change anything there? The answer is no, you don't change anything, because you can always select a region on the boundary such that you push the unitary operator ux to the boundary in a way that it doesn't intersect that point. So like if I select a point here, then I will represent my operator in a different way. I push it to the other side so that it doesn't intersect with y. So as long as I find a way to push the operator ux to the boundary without passing through y, then I don't influence anything at y. But when you look at bigger regions, that's not the case. Like if I define my operator b not at a single site y, but I allow it to be a multi-site operator. Let's say this example. So let's say I look at operators that live on these 6 yellow dots. So it can be an operator that applied to the 6 yellow dots at the same time. Then there is no way to push the unitary operator x to the boundary without using any of them. You have to use part of them, because I basically draw a circle enclose the x. And that tells me that actually this bigger region is sort of in the future of x, although each smaller region is not in the future. So this tells me why, like on one hand, I can have some kind of a time-like causality structure when you look at like regions, but when you look at small disks, small point or neighborhood of points, then every point is space-like separated to another point. Like if you draw concentric circles, then there is a sense that this direction is like time. The radial direction is like time. But on the other hand, there is no light cone. There is no particular time like difference between time-like and space-like directions. Okay, so in summary, we have shown several key properties. Like the causal structure in general depends on the initial state, and it generally is not local. And there is a particular case of the initial state dependence, which is what I call like the maximally mixed region. A maximally mixed region is always a sink of time error, which means that like if you have a region that's maximally mixed, then it cannot be future of anything. Like there's nothing happening going out of it. So. Okay, so I just want to briefly mention, since I'm, when did I start? 2 or 3 minutes. Less than 3 minutes. Oh, okay. So I just want to mention that one application of this is when we apply the tensor networks to the tensor network approach to holographic duality. You have these tensor networks that gives you a mapping between bulk and boundary. So we have these red bulk legs that describes the code subspace degree of freedom. And there is an isometry from them to the boundary. So in that case, then since we define this mapping between degrees of freedom, we can apply that to states of the boundary at a different time. In other words, we can pull the boundary time evolution, we can pull that to the bulk to define the bulk time evolution. And naively, that defines the bulk time evolution that's very non-local, because the mapping, like you map the things to the boundary, evolve it by the boundary Hamiltonian, and map it back to the bulk. It looks like the mapping is very non-local. But if you do this calculation and check the causal influence, you do something unitary here in the bulk point, and then pull it back to the boundary, map it back to the bulk, and look at which point it influences. Actually, there is a sort of a light cone that the influence doesn't go out of that point. And that's because you can run the same argument as what I did in the equal time case. Like the same reason why these 2 points looks like space-like separated. You can push operators to the boundary without using the other point. When you have 2 operators at different time, you can run the same argument, and you find that there is only a small region that you can influence. This is, this is in a previous paper where we didn't use this causal influence definition, but we just argue, we just show using the commutator between operators that this is true.
You made some assumption about the boundary yellow tensors.
This one?
Yes.
The time evolution, yeah.
So you made some assumptions about that it's local and so on and so forth?
I assume the yes, thanks. I assume the boundary, yeah. So in this case, we assume the boundary has a finite speed of light. So there's 3 assumptions. The boundary has a finite speed of light, and there is this isometry between bulk and boundary given by the tensor network with the local reconstruction properties. And the third assumption is the time evolution preserves the closed subspace. So since I'm out of time, this will be the last example I will mention. Like if you think about the quantum teleportation, then in this is just an older problem, and we just understand it in this new quantity we define. So if you have some C and you teleport it by preparing an EPR pair of A and B, and you teleport C to here. Then if you think about a unitary applied to C that's right before the teleportation happens, then what happens is, of course, like it will not influence anything here because it teleports to there. So it will only influence because you change the state of C. So if you leave here, you don't know anything, but if you leave here, you see the influence of that. So the event X will only influence that smaller yellow light cone rather than the ordinary bigger light cone. But if you prepare a wrong state here, then of course teleportation may fail, and as a consequence, the event X will influence everything in the ordinary light cone. So you see what happened again is like you prepare a special initial state, and as a consequence, you remove some states from the future of some states. So teleportation is really, you didn't add anything to the future light cone, but you remove something from it. And like, for example, if you take regions Y1 and Y2, they are both outside the future light cone of X. They are not in the future of X, but the union of them is in X. Because of course, if you know both, you know state of X. So this is another example where you have non-local causal structure. Okay, you can also try to do more on the formalism side, like try to figure out something. So I will skip these because I'm running out of time. But one thing I want to mention is we can define some criteria of the causal influence that can be more easily calculated. Like this, so far I have been talking about putting a particular unitary and then measure something at Y to see whether there's influence. So the simple measure will be you just average over all the possible insertion of operators, and then you get something which looks like a second Rényi entropy quantity, but it's different. Like at X and Y, you are inserting different operators because the key thing is that it's not bidirectional, right? It's not symmetric. Like X influence Y in general, Y do not influence X. Independent from the details here, it just means that if you contract your network with you contract everything in your network except the links X and Y, you can define this super density matrix RXY, and then there is this super density matrix. There is some entanglement property of that which gives you the average causal influence. And the advantage of having this measure is you can calculate things numerically. Right? Like we can take a spin chain and calculate that. And then you see, like when you look at a high temperature, even within the light cone, the influence goes to 0. It's a consequence of the chaotic time evolution being very non-local. It takes anything local to very non-local, so locally you do not see the influence. And then you can do similar calculations in the stabilizer tensor network and get the same thing. Like a local thing has a very little influence, and then there is no influence at all. So that's all I will say. And in general, we learn that the causal influence, if we define it in a way that's measurable, then in general it's different from the classical case. It depends on the initial state, and it's not local. And I just want to emphasize that although we use tensor networks to be concrete, this concept actually doesn't depend on the particular discretized formalism. Like, for example, in the spin chain case, time is continuous. We can still define these things. And so there are many open questions, like, is there a better measure? Are there other measures of this causal influence? And does it say anything about black hole paradox and so on? Okay, thanks.
Hi, I have two questions. The first one is, you know that some people in quantum information community are also working on quantum Corot relationship. They work by treat space and time on an equal footing. There are some formalism like pseudo-density metric formalism, process metric formalism, discrete Wigner function formalism, and also formalism of quantum conditional state. I'm wondering that do they have some relationship with your work from the tensor network perspective? It seems to me that it may relate to process metric formalism.
I see. I would love to learn more. Yeah, I don't know any of the ones you mentioned, but certainly it's very interesting to study the relation between them. One thing I happen to know is there is some discussions about complete causal, like common cause of, like you have two events, whether there is a common cause of them, and that has been generalized to quantum case. But I haven't figured out the relation between that and our work. Maybe you can tell me later about it. Yeah, thanks.
Another question is about the initial state dependence. In fact, my supervisor has a work 10 years ago. He suggests that quantum entanglement in time do not depend on the initial state. So I'm wondering that the quantum Corot influence you mentioned about has some relationship with entanglement in time.
I'm not sure what's the definition of entanglement in time, although I like the point of view that I mean, like when I talk about this super density operator, this is another thing that Jordan and I and Chao Ming and Frank Wilczek, we are collaborating on. We try to it's more like building a general formalism of generalizing the concept of states to space-time. Where we can think all the correlations as a form of entanglement. So you see, you can say this is like this definition of the average causal influence. It's like a baby version of trying to show that this thing is related to some quantum information, like some entanglement property of some state you define in space-time. But you probably have other measures of entanglement that's related to the causal influence.
Thank you.
I don't know. Yeah.
Hi. Yeah. I want to suggest that there's an exact classical analog of your property that there was an initial state dependence on your causal structure. Mm-hmm. So if I took just a random bit and encoded that into a repetition code, just 3 copies of that bit, it would have the same property that you described. I could flip that bit, and any one of the 3 copies that I made would still look completely mixed, but you would be able to see the effect of my flipping if you look jointly on all 3. So
that's like basically classical error correction code versus quantum error correction.
Exactly.
Yes.
So I'm just wondering, you were arguing that the quantum case is different, and how is it different in light of that sort of classical example?
I think I mean, I don't know, but my when I say the quantum case is different, what I mean, okay, so let's say, for example, in this case of quantum teleportation, this is basically the same as that error correction code case, where I encode this information locally to different parts, so that I cannot see it locally. So I would say, I mean, you can do something like this, the classical version of this, but somehow you cannot make the information completely inaccessible locally, because we know, like it's like in this quantum case, I cannot. I mean, it's completely safe to. We can share some entangled state, and then there is no way to get the information locally. I thought in classical case we cannot do something like that, and that will be the difference. That in the quantum case, by preparing quantum entangled pairs, I can really change the causal structure, because I cannot just change to a. I cannot by allowing to some very general things to do here. There's still something that I just absolutely have no idea about locally. But I really know very little about quantum information, so I don't know.
Thanks.
Yeah.
Hi, can you just go back to your definition for 1 second?
Mm-hmm.
I want to make sure I understand.
Here.
Oh, yeah.
Yeah.
So I guess, and then you maximize it overall.
Well, there's different measures. Like the average one is
I see.
one measure, and the maximized one is another measure.
I see. But those are like differences of Born rule probabilities depending on whether or not you insert certain operators, right?
Yeah.
So it seems to me that since you're allowing mixed states, you should also allow a purification to a larger system.
Uh-huh.
Because, I mean, I think what you actually want to do is maximize over a larger space and use what's called a completely bounded norm. I think you'll get a more natural.
Do you mean to allow? Like what do you want to change? You want to allow this U?
I just want to add rho. I just want to add a purifying system
to rho.
To rho. Yeah.
That should be okay. But do you want these U and A's to apply to this auxiliary system? That will be the thing that makes a difference.
Yeah. So you'd have to make choices about how to handle the effect of those things on the auxiliary system. But I think that would allow rho to share correlations with some environment. And now you're asking, it's somehow a bit more stable to ask this question, because you're asking it. I mean, it's known that you can change the answers to these questions about, how much two probability distributions are distinguishable, which is essentially what you have here. You have the Born rule probability distributions, and you're asking how distinguishable are they. That distinguishability changes if you add a purifying system. So you'd be allowing more general measurements in order to see that effect, but it might be a more stable. It might make some things easier to calculate and more stable.
I see.
Anyway, it's just a thought.
I would like to learn more about that. And it's certainly true that if you allow a bigger system and you allow, say, A to apply to the bigger system, then the causal structure can certainly change. So I mean, but that's also a concern that I'm not sure whether that just like you have some local influence in some system. Maybe by including some bigger system, you can always make the influence local. I don't quite understand that part. Mm-hmm.
So if we go back to the teleportation example, maybe the kind of classical analog would be to have, instead of sharing entanglement, you'd share a random bit. Mm-hmm. And now the message comes along, and you, instead of doing this Bell state measurement, you XOR the message with the random bit, and you send that along. And doesn't that now have exactly the same properties here? So if I just have access then to Y1 would now be the XOR of the random bit and the message, but I'd need Y1 and Y2 being the classical bit in order to access the information. So would you say there I've also altered the causal structure or the light cone structure or something?
question about the classical case?
Yes, about the classical case.
I mean, I guess it's a...
In the classical case, the information coming in C can be reproduced all over the place in by the tiniest little signals, and can be cloned. It can be just gravitational waves, if nothing else, in a completely classical theory will carry off all the information about C into that forbidden region there, and somebody with sufficient power to be able to measure it could reproduce everything by measurements in that what we call the forbidden region over there.
Yeah.
Classical physics can never completely forbid you from detecting what came in by looking in the forbidden region.
Yeah.
You make a pretense that you can't measure certain things or you can't know certain things, but there was things that in classical physics you can know. Whereas in quantum physics, because of basically I guess it's the monogamy of entanglement, you simply can't, in principle, you cannot know what's going on.
Yeah, so I completely agree with Lenny, and so let me say it in slightly different words. So yeah, I think what you are saying is I can design a classical system where I locally do not know anything about what I put in, but I can always, I can perturb the system by sending some other signal that measures what is the qubit here, and that will influence this future light cone. So there is no way to completely remove the influence in the general dynamics if you allow me to try different things. But in the quantum case, there is a way to remove that possibility, because if you teleport this thing there, then there is no way to locally detect anything here. So, but in other words, what I'm saying here is if you do this teleportation experiment in your lab, and then you see a photon is teleported from here to here, I'm not going to say, okay, you have changed the causal structure of the space-time. Why? Because there's many other photon states that you can have here which are not teleported. So when you measure your space-time, you can use photons with different frequencies and so on, and only one of them is teleported. That's why we usually don't think that the space-time geometry is changed. But only when you take all the states here and then you teleport them, which is the ER equal to EPR case, where you really change the geometry. And that's the case where I would say there is no measurements that will tell me there is no measurement that will here that will be influenced by UX. So this geometry has been changed. So maybe that's the point. In this system, I have been assuming that this is the only qubit living there. But in the lab system, you have many qubits, and if you have most of them not influenced, that's why we usually don't think that this geometry is influenced. But in the classical case, you sort of are. You always have that background there. You cannot completely remove it.
So a quick comment that you seem to be telling me today that you're reinterpreting quantum error correction as taking the environment out of the ability to influence the output of a noisy channel.
Yes.
Great.
I think that's a good summary.
Do you know whether you can reformulate quantum error correcting codes completely under your definition of causal influence here?
This is basically all the things I know about quantum error correction code. So, sorry.
If there are not other questions, let's thank the speaker again.
Thank you.